So today we're going to be finding the domain and range of more functions. So for the do now, what I want you guys to do is just do 1 and 2, pause the video, and play it once you are done. So number 1 states, find the values of x that make the following function undefined. Remember, undefined is when you divide a number by 0, because you can't divide by 0. So what I would do in this case is set x plus 5 equal to 0, because we want to see when it is 0, the denominator is 0. Subtract 5 on both sides, and you get negative 5 is when f of x is undefined. And for number 2, find all the real values of x that will make the following function imaginary. Remember, imaginary when it has a negative number, when it simplifies to a negative number inside the radical. So 2x minus 20, if it's going to be a negative number, you don't just want to set it equal to a negative number. We want to do the overarching rule. So it would have to be less than 0. So 2x minus 20 is going to have to be less than 0. So we solve an inequality for this one. So we're just going to solve it, continue to solve it, plus 20 on both sides. You get 2x is less than 20. Divide 2 on both sides, and you'll get x is less than 10. So whenever x is less than 10, that is all the values of x that will make that function, f of x, imaginary. This is pretty much what we're doing today, just applying it to domain and range, which is exactly what we just did. So what should I be able to do by the end of the day? I can algebraically find the domain and range of linear and square root equations, and I can algebraically find the domain of rational equations. Let's go to the next page. So let's look at the graphs of what we did in the do now. So f of x equals 2 over x plus 5. We'll get to graphs like this later on in the year, but I just graphed it for you guys so you can see the graph of it, and we'll actually be graphing this later on in the year. So looking at the graph, I want you guys to take a minute or two. I want you guys to write down, how does this graph show us the domain of this function? Pause the video if you haven't, play it once you're done. So if we look at this, you notice how the lines, so the red lines, that's a bad trace, the red lines are our graphed equation. So it's going to look like this. Those lines are never crossing the line x equals negative 5. So there's never going to be a point when x equals negative 5 on this graph for this equation to f of x equals 2 over x plus 5. So that is not going to be in our domain. So how does this graph show us the domain of this function? Well, there is no point when x equals negative 5. So we know the domain is not going to include negative 5. So there is no point. When x equals negative 5. But you can see that our graphs, the red is the graph of f of x equals 2 over x plus 5. You can see our domain is including every other number, because we go as far left as negative infinity, as far right as infinity. So our domain here is going to be from negative infinity, and then you can't say to infinity because negative 5 is not in our domain. We actually don't have a point when x is negative 5. So we're going to go from negative infinity to negative 5, and then we're just going to jump over negative 5 and start back up on the other side of negative 5 to infinity. And how does the table of f of x equals 2 over x plus 5 support our findings? Let's get the calculator out And let's check out what the table looks like. So let's take a look at the table of our function f of x equals 2 over x plus 5. So I'm going to graph that in our calculator. Whenever you want to graph, you press y equals. Make sure you clear everything from your graph. There's nothing here. So I'm going to press alpha, y equals, n over d. That's how you get the fraction. 2 over x plus 5. And when we check the graph out, looks exactly the same as the graph we have here. And now let's check the table out. So the table, you press second graph to get to the table. And look at that. As x increases, we always have values for y. The y is getting smaller and smaller. But let's take a look at when we have an x of negative 5. What's happening there? There's an error message, but it continues after negative 5. So that error message means there's no point at negative 5. So how does the xy table of f of x equals 2 over x plus 5 support our findings? Well, when x equals, that should be a negative 5. The xy table has an error message. So you could also say there's no point when x is negative 5. That works as well. And now let's take a look at what is the range of 2 over x plus 5. Well, we can see the lowest, and it keeps going. So you can put arrows on the end of all these because it keeps going and going. So the lowest to the highest, and make sure you look and see if it's skipping over any points. So it goes down all the way to negative infinity because this line continues, and it goes all the way up to positive infinity because this line continues, but doesn't look like it appears to cross the x-axis here. There's an asymptote there. An asymptote we're going to go over further down the road, but it's a line that our graph doesn't cross. So you see the two curves here aren't crossing when y is equal to 0. So that is going to be not part of our range. So we're going to do something very similar how we dance around the negative 5 for our domain. We're going to do the same thing in our range for 0. So our range is going to be from negative infinity to 0, but we don't include 0. So we use a parenthesis, not a bracket, and we kind of like dance around 0. So we go from the left of 0 to the right of 0, but we don't include 0 in union with 0 to infinity. And you could also write that as all real numbers such that y doesn't equal 0. There's a lot of different ways you can write this. You can use set builder notation, but any equivalent way works. Now let's go to number 2. Number 2, we have our second function, our second relation from the do now, and we graphed it here. So we've graphed square root functions before. So I want you guys just do the next 3 questions. Pause the video and play it once you're done. So how does the graph of square root 2x minus 20 show us the domain of the function? Well, we don't have any x values that are less than 10. If you take a look here, this is our beginning point, and that's at 10, 0. So we're not going to have any x values that are less than 10. So there are no graph points where x is less than 10. And our domain in this case would be 10 to infinity, and you want to include the 10 because there is actually a point at 10, 0. And how does the table of this graph support this? So let's go over to our calculator again and check out our table. So I'm going to graph square root of 2x minus 20. Check the graph out. It should look like the graph above. Oh wait, our window's different. Our x maximum is going to about 25 here, so that's what I'm going to change my x maximum to make it look like the graph in the notes, and it looks just like the graph on the notes. And let's take a look at our table. So second graph table, and look at all the error messages. That's going to be for everything less than 10. Yep, and then at 10, we have 10, 0, so 10 is part of the domain because there's a point at when x is equal to 10. So how does that support our findings? Well, for all values of x less than 10, the y values have error messages, or there's no points for any x value less than 10. And what is the range? Well, lowest to highest, and count this if there's any skipping, like there was skipping in the last one, but there's no skipping in this one. The lowest point is 10, 0, so we start at 0, and it continues to go up forever. So that would be from 0 to infinity. Let's go to the next page. So we want to determine the domain of the function f of x equals 3x over x plus 1. So we want to see if there's nothing restricting our domain, it's just going to be all real numbers, or negative infinity to infinity. But there is something restricting our domain here. Let's take a look at the numerator and the denominator. So looking at the numerator, that 3x in the numerator, that x can be anything. That's not going to cause any restrictions. But let's look at the denominator. The x plus 1 is where we're going to get some restrictions, because the denominator cannot equal 0. So what we want to do is set the denominator equal to 0, and we're going to see when it cannot equal 0. So set it equal to 0, subtract 1 on both sides, we get x is equal to negative 1. So that is when the denominator equals 0. Remember, we actually do not want the denominator equals 0. So that's going to be our only restriction. It's just going to be negative 1. So our domain is going to be negative infinity to negative 1 in union with negative 1 to infinity. You could also write this as all real numbers, such that x does not equal negative 1. You could also write it like that too. Either of those ways are completely fine for the domain. And if you think about the graph of this one, it's going to be that hyperbola, which we're going to get into more later on. But it would look, here's negative 1 right here. It would look something like this, where it doesn't cross. There's no point when x is equal to negative 1 on the graph. How about the next one? The domain in range of 2x plus 1. F of x equals 2x plus 1. I'll give you guys a minute to think about this, see if you can figure out the domain and the range for f of x equals 2x plus 1. Pause the video and play it once you're done. So, is there anything restricting our function? No, there's not. Think about it. It's just a straight line with a slope of 2 and a y-intercept of 1. So our domain, there's no restrictions on it. Our domain is all real numbers, or you can say from negative infinity to infinity. And same with our range. It goes as low as negative infinity, as high as positive infinity, and there's no skips from in between there. So the range would also be all real numbers. So let's look at the domain and range of f of x equals the square root of x minus 3. So we have a square root function here. If we want to maintain real numbers, there is going to be restrictions that we need to take into account. So inside of the square root cannot be negative. So x minus 3 has to be greater than or equal to 0. And that ensures us that we have a positive number or 0, because the square root of 0 is 0. So I'm going to solve for x there. Add 3 on both sides. You get x is greater than or equal to 3. And that's our domain. So domain is all real numbers. And there's a couple ways you can write this. All real numbers such that x is greater than or equal to 3. You could also say brackets 3 to infinity. That's fine too. There's a couple other ways you can write this. And the range Well, the lowest the range can be, think about f of x. If we do f of 0, actually the lowest x value we can have is 3. So if we plug in f of 3, that would be a square root of 3 minus 3, which is the square root of 0, which is 0. So that's the lowest we're going to get. So in the highest we're going to get, you can plug in as large a number for x as you want, and the range will keep on rising. So the range is going to be all real numbers such that y is greater than or equal to 0. Or you could say the range would be from 0 to positive infinity. Both those are equivalent expressions. And also, if you think about this, you could also graph this equation. And just a quick sketch of it, it's going to look something like this. So it's going to continue to rise, but it's going to start at the point 3, 0. So it's not going to go anywhere below 0 for the y. It's not going to go any farther left than 3 for the x. And the last one on this page, determine the domain of the function f of x equals 1 over the square root of x minus 3. So let's take a look at that denominator, because that's what's going. 1 doesn't restrict the numerator. There's no restrictions in that numerator, but look at the denominator. There are going to be some numbers that we cannot include in our denominator because it's going to make our denominator 0. But also think it's a square root, so we can't have the square root also be negative. So you could do this one step at a time, or you can combine both stipulations. So what I'm going to do first is, we know that the square root of x minus 3 cannot equal 0. But we also know that x minus 3 has to be greater than or equal to 0. So when you combine both of those, it can't equal 0, so we don't want to say it's greater than or equal to 0. So we're just going to say x minus 3 is greater than 0 in this case. It can't equal 0 because the square root is in the denominator this time, and that would make an undefined number. Well, it would just be undefined. So when you solve for it from here, you add 3 on both sides, you get x is greater than 3, and we're just finding the domain here. So that's the domain. Domain is the all real numbers such that x is greater than 3. Or you could say from 3 to infinity. That works also. And once again, I just want to point out, why does it not include 3 when we included 3 on the one above? This one's a little different because our square root is in the denominator this time, and we can't have our function be undefined, so we can't have a 0 in the denominator. Let's go to the next page. So determine the domain of the function f of x equals the square root of x minus 2 over x minus 7. Take a minute. I want to know what's a little different about this problem than the ones we did before. Pause the video and play it once you're done thinking about that. Here's what I was thinking. We have a square root, we have restrictions in the numerator we have to account for, and we also have restrictions in the denominator we have to account for. So let's first look at the numerator. You can first look at the denominator if you want to, but I'm just going to choose the numerator here. So we have the square root of x minus 2, and I know that has to be greater than or equal to 0, because the inside cannot be negative, or else we have an imaginary number. So that it has to be greater than or equal to 0, which means if you square both sides, x minus 2 has to be greater than or equal to 0. Just solve for x there. So we know one stipulation is x has to be greater than or equal to 2. Now let's take a look at the denominator. So the denominator is x minus 7. We know if that's in the denominator, our denominator can be negative and positive, but it can't equal 0 unless or else we are going to have no solution. We're going to have an undefined. So we're going to set x minus 7 equals 0 to see when it is going to give us a undefined. So I'm going to add 7 on both sides, and we can't have x equal to 7, or else we'll have a 0 in the denominator. So we our domain must satisfy both rules, or both stipulations. So we have x is greater than or equal to 2. You could think of this as an inequality if you want to. So x is, here we have 2. It's going to be greater than or equal to 2. But, when 7's there, we can't actually equal 7. So it's going to be like an open circle there. And then it keeps going because we can have any number greater than 7. So our domain is going to be, and I'm going to write this in interval notation. You could also write it out with words if you want to. It starts at 2, and then, wait, we can't have 7, or else we're going to have, it's going to be undefined, and there's no point there on the graph. So then we skip around 7, and it'll be from 7 to infinity. Check your brackets, check your parentheses on that, and that would be our domain. That's what it would look like as an inequality graphed, but you don't have to actually graph that if you don't want to. And the last one, I want you guys, pause the video. I want to see if you guys can do this one by yourselves. Pause the video, take, 3 to 5 minutes, find the domain of this function, and play it once you're done. This one's very similar to the previous one. We have stipulations we have to think about in the numerator and the denominator because there's restrictions in both. It restricts our x values or our domain. So let's first just look at the numerator because that's on top. The square root of x plus 5 has to be greater than or equal to 0 because we can't have a negative inside of the square root. So that would just be x plus 5 has to be greater than or equal to 0. Solve for it from there. I subtract 5 on both sides. I know x has to be greater than or equal to negative 5. But we also need to check out the denominator's restrictions. The inside, x minus 4, has to also be greater than or equal to 0. But wait, it's in the denominator. So, not just greater than or equal to 0, but it also can't equal 0. Because if the denominator is 0, then it's undefined. So it's just x minus 4 is greater than 0. Add 4 on both sides. You'll get x is greater than 4. So we have to satisfy both of these stipulations. Both, you can say rules or stipulations. So we have x is greater than negative 5 and x is greater than 4. Well, it turns out, we can't have x just greater than or equal to negative 5. It's just going to be x is greater than 4 because 4 is greater than negative 5. So we have to just go with that second rule. So that would be from 4 to infinity because all those numbers also are greater than or equal to negative 5. But we can't go lower than 4 or else our denominator is going to be imaginary or undefined. So we just have the checkpoint after this. There's 6 functions here, or 6 relations that I want you guys to find the domain and range of 1 and 2, and then find the domain of 3, 4, 5, and 6. Pause the video. This takes some time. Take 10 to 15 minutes. No rush on this. And then play it once you're done, and we'll go over it. Here's 1 and 2. If you look at 1, it's just a square root function. So our range is greater than or equal to 0. In our domain, the inside of the radical, the radicand, has to be greater than or equal to 0. So when you solve for it, you get x is greater than or equal to negative 13.5. And number 2 is just a straight line. It's in y equals mx plus b form. So it's just going to be the domain is going to be all real numbers, and so is the range. Looking at number 3 and 4. What is restricting our domain? We're just finding the domain here. Well, the numerators in both cases aren't restricting the domain at all because the numerators can be positive, negative, they can be 0, but the denominators cannot be 0, or with number 4 can also not be negative because it's radical 4x minus 23. So you have to take that into account, and you can write it either way. And 5 and 6. So 5 and 6 have restrictions in both the numerator and the denominator. So if you take both of those into account, put them both together, look at 5, we kind of have to dance around x equals 6 because the denominator cannot equal 0. And then looking at number 6, you see there's two stipulations, x is greater than -1 and x is greater than or equal to 2. But if x is greater than -1, it's also greater than or equal to 2, but we can't have it lower than 2 or else it doesn't fulfill this stipulation, this rule. It would make the numerator imaginary. So we have to go with just that rule that x has to be greater than or equal to 2. That's it for these notes.